In this section of 873, we will discuss exponential smoothing with the presence of a seasonal component. We have seen previously that we can use regression models in the form of a dummy variable or trigonometric model to model seasonal data. There will be situations where the previous models do not fit well. In these cases, we will use seasonal exponential smoothing techniques. You should realize that the techniques that we are going to talk about are only as good as the data that we have at the present. Recall that is the weakness of smoothing techniques. The regression models are much more powerful since we can check assumptions or whatnot. That being said, for seasonal data, we will focus on the Holt-Winters method that we discussed in the previous section. There are actually two types, multiplicative and additive. Let's first discuss the additive technique. The additive Holt-Winters technique is useful when the amplitude of the seasonal pattern is independent of the mean. So if the range of the seasonal behavior is constant regardless of the mean value, then we employ the additive version. The function is written with a trend piece, LSUT, and a seasonal piece, SUT. Notice that the linear component has both a constant and a slope term. The seasonal adjustment is constant across the length of the entire period, here denoted as S. We also assume that the sum of the seasonal adjustments is 0. The forecasts are determined by using first-order exponential smoothers with not necessarily the same discount factors. The lambdas do need to be between 0 and 1. We will update the estimate for the trend piece using the equation given on the slide. Notice that this estimate includes the seasonal piece for time Ts and the trend and coefficients from time T1. What does this mean for the fits in this situation? Now use the updated linear piece to determine the updated seasonal and coefficient pieces. Notice here that we have different lambdas for each term. So in total, we have 3 lambdas for the seasonal exponential smoothing technique. To find the tau step-ahead forecasts, we use the pieces that we found in the previous slides in the equation given on the screen. The only problem now is what to use for starting values. For the starting values, we will utilize the estimates from the estimates of the model given in the slide. Now let's talk about the variable I. I is called an indicator function. It is defined on the screen. If t is equal to I, then I equals 1. Otherwise, I is equal to 0. The starting values are now just the estimates from the fitted model. The starting value for the trend piece is the intercept term. The starting value for beta 1 is the slope term. The starting value for the seasonal piece is the negative of the sum of the gamma terms. We choose lambda in the same manner as we did for the non-seasonal exponential technique. First, we find the SSE for many combinations of lambdas. Then we chose the set of lambda that minimizes this quantity. The problem here is that there are many possible combinations of the lambda. Luckily for us, there are computer packages that will do this for us. Here is an example considering the sales of clothing in the US from Gen 92 through Deco 3. Let's create the model using the data from 1992 through 2002 and assess its predictive ability using 2003. Here is a plot of the data over time. Does the series exhibit a seasonal pattern? Is there a trend? What about constant variance? Based on the plot, it would seem that there is a seasonal pattern. The trend is a little more fuzzy. Now we need to determine the type of seasonality. Is it additive or multiplicative, and how do you tell? To determine which type to use, we will create a plot of the average response based on each season and plot it against the range of the data for each season. If there is a strong linear relationship, then we use multiplicative. If not, then we use additive. Here is the plot of the averages versus the ranges. Since there is not a strong linear relationship, we would choose additive. Next, we need to find the values for the 3 lambda. Most higher-level computer packages will determine these for you. Based on the package R, using the function Holt-Winters, the alpha, beta, and gamma values, lambda 1, 2, and 3 respectively, found by minimizing the SSE are given in the slide. Here is a plot of the data along with the fits after the smoothing process. Notice that there are no fits for the first month. Ask yourself why that is. Now here is the addition of the PIs and observations for the year 2003. Let's get a closer look at these. Notice here that the PIs are the red lines, the fits are on the black line, and the black cycles are the actual observations for the year 2003. Does it seem like all of the responses fall in the PIs? Here is a table to give us a more exact answer. Based on the table, all 12 values seem to be covered by their respective PIs. We should conclude that the smoother does an adequate job forecasting the year 2003. Now let's talk about the multiplicative version of seasonal exponential smoothing. You should notice the difference right away between this function and the additive one. In this case, we take the product of the two components instead of the sum. The restriction on the sum of the seasonal pieces is also different. For the multiplicative technique, the sum of the seasonal pieces should be s, whereas in the additive case it was 0. Just as with the additive case, we will need 3 discount factors, which will all need to be between 0 and 1. The trend piece will be updated based on the equation in the slide. Then we use the updated trend piece to update the slope and seasonal terms based on the equations in the slide. Notice here again that we use sub TS to update the seasonal piece. What significance does this hold? Finally, we can create a tau step ahead forecast from the equation in the slide. The starting values are found in a similar manner as with the additive technique. You can find these equations in the textbook on page 216. Let's look at an example of liquor sales. We have data on this response from Jan 02 through Dec 04. Let's create the model using the data through 03 and check its forecasting ability with the 04 results. Here is a plot of the data. There is a seasonal pattern present. Let's check to see if the seasonality is multiplicative or additive. Here is a plot of the averages versus the ranges for the data. From the plot, it seems that there is a strong linear relationship here. We should conclude that the correct technique to use would be multiplicative. Next, we need to determine the discount factors. Based on minimizing the SSE, we find the discount factors given in the slide. Here is the initial plot with the fits. The smooth data seem to fit well. Let's add the 2004 data. Here is the plot including not only the fits, but also the PIs and observations for 2004. They seem to cover, but let's get a closer look. Based on our zoomed-in plot, all of the PIs cover the observations except for the month of August. Let's look at the actual numbers. We can see that for the month of August, the observation is smaller than the lower PI. So we can say that the PIs cover for 11 out of 12 months. We can conclude that the smoother does an adequate job of forecasting 2004. We should investigate the month of August to see if anything unusual occurred. Next time, we will begin our discussion of the Box-Jenkins techniques.